Okay, so we had this thing. We sent people to the movie theaters. They looked at the movies. They wrote some stuff down, some information about themselves, how much they liked the movie. In problem 1, we are trying to do kind of what we were doing last time. This is what most people do with this kind of movie data. Try to use the information about who were the people and did they like the movie or not to try to figure out what kind of people will like the movie. This is a blank learning problem, and 16 people out of 19 said supervised. Supervised learning. Does someone want to tell me why they think it's supervised? So big majority here, almost everybody thinks it's supervised. Why is this a supervised learning problem? Yeah?
Yeah, because we already have the demographics, the data, and along with it we have the ratings.
Right.
So it's like the predicting value we do have it.
Right. Okay. So I really like the way you said predicting value at the end, right? So we have kind of two separate things. We have the information about the people, and we have the rating, and we're trying to predict the rating using the information, and we have both. So this is a supervised learning problem, right? We're given both things, and we're trying to, for unknown people, somebody else comes off the street, we get their information, we try to predict. That's exactly the setup for supervised learning. Okay, so very uncontroversial here, 16-3. Supervised learning is the correct answer for this one, so good job if you got that one right. Let's see, did people think it was classification versus regression? This is very similar to what we did last class, and let's see what people decided. So 13 people think it's classification, and 6 people think it is regression. So maybe somebody from, this one's a little bit closer. Maybe somebody from either group want to tell me why they think it is what it is? I'll hear from both groups. So either group can go first. Yeah?
The way I thought about it is, we can say 1 to 3 stars is enjoyed the movie, and 4 and 5 stars. Sorry, 1 to 3 is not enjoyed the movie. 4 and 5 stars is enjoyed the movie. So
I see. I see. So you did a split, and you said the thing we really want to do is just figure out, like, did they enjoy the movie or not? And we're just going to split it into 1 to 3 stars that's not enjoyed, and 4 and 5 are enjoyed. So you are on team classification. All right, very, very good answer. And yeah, anybody else? Yeah.
So I thought it is a regression problem because right now we are focusing about advertising, and I think that just hardline classification can't work here, like enjoyed or not enjoyed. How much he enjoyed. He can even enjoy 7-8 movies, but which movies he enjoyed the best, so then according to it Netflix can advertise it or any other company can advertise it. So it can be rated on a scale of 1 to 10. And also there are a lot of variables that we need to take into consideration. So I think multivariable regression can fit it very easily.
Okay, this is great. So there are some things I really love that you said. One of them was that, look, we're talking about advertising, and it doesn't just matter did they like it or did they not like it. It also matters how much they will like it or not like it, right? Because maybe I have $1 to spend on my advertising budget, and I don't have enough money to advertise to everybody. So maybe there's too many people who I think would like the movie. Maybe I want to hyper focus on the people who I think will really like the movie, right? So that is leading you towards thinking of it as a sliding scale, where some people like it more, maybe someone likes it a little bit less, someone likes it a little bit less, and that is thinking about regression for you. There are a couple other things you said. One thing you said is there are a lot of variables. I think that is totally true, but I think a lot of variables doesn't tell you if it's classification or regression. So you can think
the model,
right.
Which model to apply.
Yeah. Okay. This is another thing. And lastly, I think you had a great suggestion, which is we can use a linear regression model. That is also a great suggestion. So if we decide it's a regression problem, we can do linear regression model. Later in the course, we're going to spend a lot of time on the linear regression model. So if you've never heard of it, you will get to know it. I do want to point out that it is an unfortunate coincidence that the word regression appears in both. So a linear regression model, it is a model used for regression, but to me, it's like a specific type of model. And this word regression, you can think of it without knowing anything about linear regression. So just make sure you don't confuse those. I'm not saying you're confused. I'm just pointing out for everybody else in the class. Make sure you understand the difference between classification versus regression and the word regression in linear regression. They are different. Okay, so we had 2 good arguments from both. I'm going to give you guys a chance to change your mind. So I'm going to open it up for a revote. You can think about which argument was more compelling, and we're going to revote on this particular one. So I'm going to close this, and I think there's a button here I press. I press repeat exercise, and then we will do it again. We'll do it again. So I'm going to run it one more time. For all the other ones, I guess you can put in the same answer you had before, or just put in a get joke answer. I really want to just focus on this one blank over here. In problem 1, what kind of problem is it? Is it classification or regression? Which do you think? Did you change your mind? And feel free to talk to people beside you, but I'm only going to give you, say, 2 minutes or something. I guess we'll do 3 because I already have the timer open for 3. But okay, so there it is. It's open again. You can change your mind. Even if you don't change your mind, you have to put in your vote again. And we'll see if people's minds changed or what the deal is. Okay. Okay, I'm doing 2 minutes. So you don't have a huge amount of time here to decide what you think. Okay, 8 people left to put in their answer in the last minute. I'm up to 12 answers. Okay, 20 seconds left. 3 people left. 2 people left. Okay. Let's see what people thought this time. And so we're going to reveal the counts. Okay, everybody's in supervised learning. When I teach the first year classes, I tell them the answer and then we revote, and then there's still like 5% of people that get it wrong. So you guys are smarter than the first year students. All right, so some people switch, but not a lot. Classification still has a slim majority. I'm going to hit reveal answer, and then it's going to reveal what I think. Okay, and I think in this kind of situation, there is no like absolutely mathematically right or wrong answer. It's not like a proof where the answer was 7 and you got 6. Like, you could argue either way, but here is the one I think it is. And I'm going to hit reveal correct answer. Supervised, and I said regression. I think it's regression. And the real reason I think it's regression, it has to do with this idea of trying to figure out the amount that people like it or don't like it. But it's also this idea that when the computer model is going to guess how much somebody likes the movie. So the computer model is going to say, I think this person liked it 4 stars. And if the computer model says they liked it 4 stars and they actually liked it 5, that's closer than if they had liked it 1 star. And so anytime you want to incorporate the closeness of numbers in what you're doing, that is a regression problem. Classification, the bins are completely separate, unless you do, maybe there's some fancy version of classification where you can do something more complicated, but on the face of it, classification, the bins are completely separate, and you just want to maximize your chance of getting it in the right bin. So that would be my model wants to get the chance of getting it exactly right as high as possible, versus regression is I want to be as close as possible. And that to me is the reason why it is regression. So we want to get as close as possible. We want to be able to identify people who like it a little bit more than other people. And for those reasons, I think it's regression. So of course you can disagree. You can think, okay, I actually do just want to know, did they like it or did they not like it? Which, maybe that's what you want. But that is the way I think about it, and those are the 2 factors for me that are the most important. Any questions or comments about that? Yeah.
I want to know if it doesn't matter the advertising purposes.
Mm-hmm.
Do you choose again the regression as well? For example, we just to know who will enjoy the movie.
Yeah. So this is, I think, in real life, you have some business goal or something that you want to do, and it's your job as the data scientist to think about how will the math problem I choose like match the business goal. And that is why there is no right or wrong answer. Like maybe it really is classification, and you want to think of like people who like it, people who don't like it, depending on what you're really trying to do. So I think, and it's ambiguous, right? Like in real life, you have more information, and you'd be able to say really one way or the other way. But yeah, there is no, So I'm saying for advertising purposes, I still think it's regression for the two reasons that I said before. Yeah. Okay. Great question. Any other questions or comments? Yeah.
Any situation this would be a classification problem?
Yeah, so it's like you said, if there was some kind of reason that you need to sort people into two buckets, and just getting the buckets as correct as possible is what you need, then it would be classification, right? So
for example, say if I want to classify people based on what kind of movies they like, say based on genre.
yeah.
So then it can be a classification.
That could be a classification. Yeah, right. So if we're the movie theater and we're going to advertise, and suppose our advertising budget is big enough that we can advertise to everybody, and we're going to either do a comedy or an action movie, and we're going to send you an advertisement for that. Then it's still advertising, still the same data set, but now it's a classification problem of which movie am I going to show them, right? So it really the fact that it's movies doesn't actually tell you about if it's classification or regression. It's like the details of what you have and what you want, and thinking about what counts, right? That is what sets it up. That's why it's not super simple. Okay. Right. Yeah. Great comments, guys. Anybody else? Okay. Let's go to the next question, which I will. Let me use the original votes. Let's use the original votes from the first time. Okay, let me move this out of the way. Okay. So supervised, and this one, I was saying it's regression. Of course, it depends on the details, but I gave you those two reasons. The next one, use pictures of the paper to help create an optical character recognition system. So taking the text that they wrote and taking a picture of it with pixels and converting that into what they wrote, right? So they wrote on paper with a pen, 5 stars. You have to turn that into the number 5. Okay, so first of all, is this supervised or unsupervised? And what did people say? 18-1 said supervised. Same thing as before. We have the data set of all the pictures. There is technically one step you have to do here that I think everybody was thinking, oh, obviously you're going to do that. That turns it into a supervised problem.
Labeling them.
Yeah, that's right, labeling them. So you need to pay some grad student to sit in the corner and label all the ones we have, and then once they're labeled, then it's a supervised problem. So it is important that we have those labels, which on the face of it, if we just have the paper, technically we don't have the labels. And sometimes labeling can be a really big job. So it's important to be aware of that kind of thing. But yeah, I agree with supervised. And did you guys say it was classification or regression? Here we are 15-4 for classification versus regression. Does someone want to tell us what they thought for either choice? Anybody else?
So I went with regression because
Yeah.
Since we are trying to calculate the exact number of stars,
Uh-huh.
so it's not like 1 or 2 buckets as you said for classification.
Uh-huh.
So I thought it would be regression for this particular question.
Okay, so you said we need to get it exactly right. Like if I say it's 4.7 stars and it's 4, like that is wrong. It's just wrong. And then you said therefore it's classification. Okay. All right. Anybody else? Yeah.
So we are dealing with characters in English here, or you can say in ASCII. So we have finite number of characters. So we need to have a classification problem, because in regression,
Yeah.
if the model confuses between A or B, then it is a disastrous. So
Right.
we need to be accurate.
Okay. So same thing as before. Like you need to get it exactly right. Saying that a 4 is a 5 is just completely wrong. It doesn't matter that 5 is close to 4, and therefore it's classification. I will point out that the data we had is always sort of discrete. So it's 1, 2, 3, 4, 5, right? So sometimes you can't rely on this finitely many things. But in this case, the second argument about close doesn't count, right? That is the reason to me it is classification. So I also went with classification. And can I reveal? If I go into present mode, if I click on one of these, reveal the answer. Okay, this was supervised. Oh, this is in the second round. Okay, click here. Okay, supervised, and let's reveal correct supervised regression, and I also went with classification. So most people got that right. Okay, let's look at scenario number 3, unless there are any questions or comments about that one before we go to scenario 3. Let's look at scenario 3. So this one is a little wonky one. There's aliens, and they are writing on the thing, and the thing is that we don't know the alien language. So what are we doing? We have the pictures, and we're trying to learn something about the alien language. So is this supervised or unsupervised? Almost everybody said unsupervised. And I think I completely agree with that. It's very similar to number 2, except that we don't have the labels, right? In number 2, we paid the PhD student to sit and label all the things we got. But there is nobody to label them here. And when there's nobody to label them, the best you can do is some kind of unsupervised thing. And maybe try to group digits that look similar, like this symbol looks similar to that symbol looks similar to this symbol. Try to group them like that, just based on the symbols alone, but based on the pixels alone. So unsupervised is what most people, almost everybody said, and I think that is correct. Any questions or comments about that one? Okay, I will say, at the end of this, I will tell you a way in which you can convert it into supervised, which is called semi-supervised, which is an exciting kind of newfangled thing. So I'll mention that in a minute, but let's before we do that, let's say, is this regression or classification? And most people said classification, although we have 7 for regression. And this, I think, is by far the most ambiguous thing in the whole thing. So when you're doing an unsupervised thing, normally you're just grouping things together. Is that a regression or is that a classification? I think it kind of depends on how you look at it. If you're saying, here are the different clusters, then that would be a classification. If you're mapping things, say, to a number line, and you say, look, there's all the things where the score was -7, there's the things where the score was -6, maybe there's a spectrum of things in between. So it could be either way. It just depends on how you think about it. So it could be either. Does anybody want to share how they thought about it and why they think it's one or the other? There's probably some creative ways of thinking about this alien problem. Yeah, here.
So I was thinking of it as a classification problem because, what can I say? Because we are clustering them together, like separating them, and they are separate characters and all.
Right.
So that's why I thought of it as a classification problem rather than regression.
Yeah. So I totally agree with that. I like that. Separate characters. So if you kind of imagine that the aliens have a language system that is somewhat similar to Earth language systems, there's probably different types of characters, and we really just want to put all the types that are the same in one bucket, put them in the other bucket. If you think about it that way, it's definitely classification. Maybe the aliens have some, the alien languages, they draw lines of different lengths, and depending on the length they draw, it means something different, I don't know, they're aliens, we don't know anything about them. So it could also be regression if you have some other way of thinking about it. Okay, fantastic. Any questions or comments about any of these? I'm going to say a word or two about semi-supervised learning, which I think was not mentioned in the videos, but is an exciting new frontier of things. Okay, so let me say a couple words on semi-supervised learning, which is not in the textbook, but is good to know about. Okay, so in semi-supervised learning, semi-supervised, so kind of a cop-out name, semi-supervised, that should be a U, they got a little close together. In semi-supervised learning, you essentially take an unsupervised problem. You had a problem that was completely unsupervised, and you are going to convert it into a supervised one. That's how I think about it. So you convert an unsupervised into supervised. So how are you going to do that? You're going to take your data that you have that doesn't have any labels. So let's pretend we have the aliens, and I'm also going to further pretend that the aliens, let's pretend that they draw with symbols. So here's some alien language. Triangle, circle, square, circle, triangle. This is what the alien wrote. And here is a different alien that wrote circle, triangle, circle, circle, square. And then here's another alien who wrote triangle, 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 circle, circle. Okay, so these are what the aliens wrote. And of course, we don't have labels. We don't know what they mean, so we can't do supervised learning. But what we can do is we can convert this data set into a data set where we do have some labels. We can create labels by masking out parts of what we have. So this is what we were given, and we are going to convert this. We're going to convert it by covering up some parts. So here is, I'm going to try the magic of computers. So I'm going to copy, paste. Will it let me copy, paste? Maybe it won't. Let's try one more time. Duplicate. Okay, that's what I want. Great. Okay, so here's what the aliens did. What I'm going to do is I'm going to cover up some of the characters. So I'm going to say, I'm going to delete this triangle, delete it, and I'm going to put this triangle as the y value. So I'm going to think of these as the x's. I'm going to delete the last character and think about it like this. So delete. And okay, really what I mean by delete is I mean replace with a blank. So let me do it a little bit more clearly. I will say blank, blank. So the problem, the original data set we had no labels, but I deleted one of the characters and I replaced that character with a blank, and then I used that blank as whatever was there as the label. And now I say, take these x values and try to predict what is in the blank. So now it is a supervised learning problem because you have x's, you have things that you're given, and things you're trying to predict. And the idea is that if a computer system is very, very good at predicting what is in the next blank, then it will have somehow understood something about how the data works, right? So even though there were no labels, this will somehow learn something about how the alien language works. And you don't have to do it with just the last blank. I did it with just the last blank here. We could keep making our data set longer and longer by doing blanks everywhere. So I could do triangle, circle, blank, square. Let me do one more. Square, blank, blank, triangle, right? So I take the first one and I can, instead of blanking out the last character, I blank out the second last one. And then the answer that you're supposed to find is circle. And so you can make a huge data set out of this by starting with some unsupervised data. You make this giant, giant data set. And then you have a supervised problem where you can try to do things. And you can do this with, this is sort of a text example. You can do it with images. You can cover up some pixels and say, please predict what pixels were there. And the idea is hopefully that your system learns something about the underlying data. So for example, maybe you would learn the pattern. Here is a pattern that is hidden in the data. That it looks like random data, but here is a pattern. After every triangle, it is always circle. After triangle, always circle. Always circle. So if you had a system that was very good at predicting the next character, it would learn this pattern that after triangle is always circle, and then now you've learned something about how the alien grammar works. I don't know. This is like the end of a sentence, and that's the beginning of the new sentence. I don't know how the aliens work. So after triangle, always circle is the kind of thing you could learn. So that's called semi-supervised learning. Why am I telling you about why am I wasting class time talking about semi-supervised learning? There is one killer example of semi-supervised learning that has taken the world by storm in the last year. Does anybody know? Yeah, this is how ChatGPT works. So on ChatGPT, they downloaded all the text on the internet, and they covered up all, like one word at a time from every sentence on the internet, and ChatGPT just predicts the next, what is in the blank. But it got so good at predicting what is in the blank that you can use it to generate text. How do you use it to generate text? Well, you say, okay, so the first word is nothing, predict the next word. You say the, and then the first word is the, now predict the next word. You say the cat, okay, what, the cat, what? And, okay, the cat and, what's the next blank? And then by just predicting the next thing over and over again, you can generate lots of text. So this is how ChatGPT works. It's trained in a semi-supervised way. So it's an important thing to know. And the really big pro, the huge pro of unsupervised or of semi-supervised learning compared to supervised and unsupervised is you can use all the really good methods from supervised, but you can have a giant, giant data set like unsupervised. You don't need to pay somebody to label. So its pros are giant data set, giant data, and can use supervised methods, which are really well developed and good. Okay. Okay, so that's why semi-supervised is important to know about. Any questions or comments about that little diversion? I think they didn't mention it at all in the videos, and we won't really do it a lot in this course, but it is good to know about. Okay.
Any cons?
Any
cons?
Any cons? Well, I think the cons are you can get a lot of data, but you do need a lot of data for it to work. So somehow the thing you're trying to find is very weakly hidden in what's going on here. So in practice, people have found that semi-supervised works great if you have these giant data sets, but if you have a small data set, it doesn't work so well. So yeah, let's put a con. Con. Sometimes requires big data. Requires large data. And I guess at the end of the day, you also maybe can't do the patterns. Like this pattern that after triangle is always circle would reveal itself in your model by whenever you have a triangle, the probability of circle would be very high on the next token. But like as a human, like it's not explaining it to you that after triangle is always circle. You sort of have to like probe it to figure it out. So maybe like hard to reason with too. Or can be hard to reason with. And that is definitely a problem with ChatGPT. Like you don't know how it works, it's just a magic box that outputs the next token and you don't know why. Okay, yeah, great comment. Yeah.
I think one of the cons would be the cost, because labeling data in a large amount may be complex.
Right. Well, so this way you can avoid making the labels. Like you don't have to pay anybody to label it because you're just covering up with the blanks. So I think the fact that you don't have to label it by hand is a big pro.
Not by hand.
Right.
But maybe pattern recognition and define something that's board for pattern with some complexity, and even if you want to do it with system or with machine, I think it needs some.
Yes. Okay. Let's add this. I think this is both a pro and a con. So a pro is no labeling needed. No labeling needed, right? Like it's all automatically labeled by what you blanked out. I double clicked and now it hates me. Okay. Let's try again. Okay. So no labeling needed. That is a pro. Oh, maybe I bumped this. Maybe that's what I actually did. Okay, we're back. Okay. So no labeling needed. I think that's a pro. Okay, that's kind of no labeling needed is a pro. But then the con is, I think, like if you need a really big model that can understand the complexities of language or whatever you're doing, and that will cost you money and be difficult. So it requires large data and requires a big model or complicated model, maybe complex, expensive, large model. Okay, or can require it. All right, yeah. Great comment. Anybody else? Okay, so let's go back to our thing. We're on this. Okay, this is what we ran before, and we revealed all the answers. So supervised regression, supervised classification, and unsupervised. I sent classification here because I was also assuming that the aliens write in characters, and the characters are different, but maybe they're not. Okay, so that was that one. We're going to move on to another exercise. Nope, I want the second exercise too. Okay. And this is, again, terminology from the videos that you were supposed to watch. So here we have an equation, y equals f of x plus epsilon, and I want you to just give me a one-word description for each of these x, y, and epsilon. There's more than one right answer, but choose your favorite for each of them, and you should be able to type in just any word. And then I'm going to ask you, what does the hat mean? So we're going to start doing some math. We're going to have these things, x, y, and epsilon, and hats, and I want to see if you know what they mean. So I'll give you 3 minutes, say, to do that. Okay, there's like 30 seconds left, so make sure you get a guess in for all of them. For number answers, we put 5, 4, 3, 2, 1, and if you don't know or don't want to guess, you can also put in the letters IDK, is what I've seen undergrads do when they don't know. But feel free to take a guess if you're not confident, but put something in, because you get these bonus points for showing up and participating. Okay, 5 seconds left. Okay, let's see what people wrote. Reveal counts. Okay, X. So lots of people said independent variable or independent variable predictor. Yeah, so independent variable, I think that is totally correct. People do call it that. To me, independent is a bit of a confusing word. Independent of what? Like, you know, so the idea is that the X variable can sort of change and the X variable will affect the Y variable. Like you have independent and dependent. So if that makes sense to you, then great, go with that. The one I like is more like these. This is great. Predictors or features. The X is the thing that is trying to predict the Y. So predictor. Features is really commonly used in machine learning. So these are the features of the thing, and the Y is the thing you're trying to predict. And I saw one other one that I really liked, which is very simple. Input variable. I really like that one too. Input variable is great. This is the input, and Y is the output. We're trying to build a machine that takes in inputs and puts out outputs. So thinking of X as the thing that goes in the machine is great. All right, yeah, input I really like too. So I think everything people wrote is great and bad at time management is the only one I would say is not correct, but great answer there. Anyway, independent or input variable, I guess the program will eat your spaces because it's assuming you're going to do one word. If you put in the slash, it looks great though. So congratulations to people who decided to put a slash. That looks very nice. Or a comma. So there you go. That's a good pro tip. Don't put spaces in. Put in commas or slashes. These are all correct answers. Very well done. Even the people who are bad at time management, they will learn. Okay. Questions or comments about the X? Let's move on to the Y. What did people say for Y? Still bad at time management. Okay. Output. Yeah. So dependent, right? So if you're thinking of X as independent and Y as dependent, that's a great way to do it. Outcome or label. This is again the way people in machine learning call it. Label is kind of sometimes reserved for classification problems when it's like, which bucket are you in? But you can definitely think of it as an outcome or a label. And yeah, output I really like as well, which 3 people also picked. Dependent variable. Predict. I think predict might be a little confusing. But again, all the right ideas here. So you guys know what you're doing. Okay, what about the epsilon? The epsilon I think is the one most people, out of all 3, is the most slippery one. What is the epsilon? All right. Some people said the bias. Some people said the bias. Some people said the error. Some people said the absolute error. This person said the irreducible error. Okay, probably they were going for irreducible error. Error. Okay, degree of error. Error residual. So this is, I think, what is confusing about this one, is it has something to do with error. It's got something to do with the ideas of like risk factor and bias, but you know there are other types of errors you can make that are not this epsilon. So if you just have the idea that epsilon is error and I'm done, and you're not thinking about like which error specifically is it, then I think you can get easily confused. And some of these that are written here are wrong, are like very misleading and wrong, and some of them are correct. Error is ambiguous. I don't know if you actually know if it's the right thing or not. So I'm going to ask you guys to do it again. Think of what kind of error. So everybody should put in something error. What kind of error is it? Or you could describe the type of error using some more words. So we'll have a revote in a second. Let me just quickly do hat, because I think hat most people usually know. Hat. Hat, okay. Estimate value vector predicted, X, expected value, estimated value, predicted output, and estimate. So looks like people are a little bit all over the place with the hat as well. So let's do a revote both for epsilon and for hat. And feel free this time to chat with your neighbors as much as you want. What kind of error is it? What the hell does the hat mean? Okay, so I'll set you guys free to revote. I will open this up again, and we'll reconvene in 3 minutes. Okay, so it's open again. You should be able to put your answer in one more time, but take as long as you need, up to 3 minutes, and feel free to chat. Okay, 1 minute. 1 minute left. I don't know. You guys are thinking in silence. Maybe you're all looking up the textbook on your computer. I guess valid strategy. Okay, 10 seconds left. Get your epsilons and hats in. Okay, let's see. What do people say this time? What kind of error? Oh, okay. This is a thing that happens. If the timer starts in the background, then later it surprises me. Okay, we can't let that happen. Okay. Let's reveal counts. Okay, x, input, okay, and epsilon, irreducible error because of model, absolute error, outlier error, error, again, not specific enough, variable error, residuals, degree of error, residual error, unavoidable error, bias, random error, and 3 people in irreducible error. Okay, so there's one here that I really like, that I've never heard before, but I think is amazing. The unavoidable error. The unavoidable error. I think that's great. They should call it that. So this error really represents all of the stuff, right? We have this model that y equals f of x plus epsilon. The f of x is kind of saying x is affecting y, right? How is x affecting y? Well, the function f tells you. You take the input x, you apply f to it, f takes in input as x and tells you how it's affecting y. So that's the f. What is the epsilon then? Epsilon is everything else. Y is determined by a lot of things. Maybe some things involve X, that's captured by F, and epsilon is everything else. So if you wanted, you could even write, you could, to be like, if you wanted to be like kind of silly, you could write Y equals F of X plus epsilon, and you could even write like epsilon is everything that is not X. Okay, right? Like epsilon is all the stuff except for specifically what X is doing. So it could be things you don't see, like maybe you make a measurement and some of the measurement is deleted or like not available to you. That could be in the epsilon. Maybe there's random chance, right? Like maybe part of the thing involves rolling a dice and then the outcome of the dice roll can be baked into that epsilon, right? Which the outcome of the dice roll you could say depends on the angle the dice was rolled at and all that stuff. All of that stuff is things other than X. All of that stuff is in the epsilon, and I think so. That's why I like the name unavoidable error. If you only have X, you will never ever be able to predict epsilon because the epsilon, by definition, is all the stuff that is other than X. So I like that name, unavoidable error, which I've never heard before. It's very creative and very nice. The typical name in the textbook for this is irreducible error. So if you said irreducible error, that is the textbook way of saying this unavoidable error. It's the error that you will never ever be able to get rid of if you only know X. It's irreducible. Even if you're the smartest person in the world and the best data scientist and you have a bajillion data and everything, you will still never be able to get rid of that epsilon. So that's why they call it irreducible. Some of these other ones I think are very common misconceptions. So I'm going to call out the common misconceptions. So don't feel bad if I call out your answer. I think they're very common misconceptions because there are a lot of different ways to talk about error. And the thing that you don't want to do is confuse this epsilon error with some of these other ones. And so some of these are just, I think, a little bit vague, like random error. So maybe you know what's going on, maybe you don't. Like it is random, but I don't know, it doesn't tell you what it is. This is one I think that we're going to spend a lot of time talking about bias and variance in the next class and next week maybe. And bias is a type of error, but it is not this error. So bias has nothing to do with this error. Bias has something to do with when we have an estimator. And there is no estimator so far. This is like a model of the universe. Bias is not the right thing here at all. Okay. What other? Residual error. So residual error, people, again, normally think of the difference between some model and the true values. And they call those the residuals. So if you say residual error, you might be mixing up, again, a type of error associated not with reality. This epsilon is some statement about reality. You might be mixing up the errors in reality versus the errors in a particular model. And again, this idea of unavoidable or irreducible is a good way to see the difference. If I was perfect and I knew everything in the whole universe and I was the smartest person alive, I would still never be able to get rid of this epsilon, but I would be able to make my residual 0 and I would be able to make my bias 0. So that's a good way to think about the difference. Degree of error, I guess that would be like how large epsilon is, maybe. Variable error, again, I think is a little vague. I don't know what it is. Outlier error, same thing. I don't know what that is. Absolute error, to me, the error, see the thing is the epsilon can be positive or negative, and to me, absolute error means how big is the epsilon. Like take the absolute value or the square or something. Irreducible.error, because of model. Yeah, I think that this is good. This is a good one. So the point is that a different person could have a different way of thinking about f of x plus epsilon. If they have a different x, then the epsilon will be different. Again, because we sort of divided the universe into x and everything that is not x. So if my x is different than yours, then our epsilons will be different as well. So I think that is a valid way of saying it. It's irreducible because of the way we said we're only going to look at the dependence on x, and everything else is in the epsilon. That's why it is what it is. Yeah, okay, great. Any questions or comments about that one? This is an important concept to know. Okay, fantastic. Let's look at the hat. The hat, estimated, function with bias, an estimator approximation, estimated value, predicted output. I think these are all great. So if you have estimated or something like that in your answer, that is wonderful. Okay, this is a good one. Expected value. In some like physics textbooks, they use hats to mean expected values. In this book, hat does not mean expected value. Hat means estimated value. And of course, one way to estimate something is to take the expected value. So there is some relation, but keep them clear in your mind, estimated or predicted is the right thing. Estimated, estimate, prediction. So anytime we see a hat, it's going to be something that depends on our data that we are estimating. And so, for example, if you see f hat, that is like, there's the world's true f that we're trying to get to, and we're going to estimate it by some procedure. We'll call whatever we end up with f hat. Okay? So that is a good one to know as well. There was one other one. Function with bias. So this is the thing. So the estimator can have bias, but just because you see a hat, that doesn't mean it has bias. Like, it could be biased or unbiased. It's the thing you estimate. Sometimes the thing you estimate does have bias, but that's not like the definition of the hat. So pretty good overall here for the most part. Any questions or comments about the epsilon or the hat? Okay, so this is like the core terminology that we're going to be building off of, is this problem, y equals f of x plus epsilon, and we're going to be analyzing how to find a good f hat. Like, that is the core of data science and modeling that we're doing for the first part of this course. And we are going to start with regression. So we're going to sort of put a pause on classification. We'll come back to classification later. We're going to do only regression for a while, and your first project is all about regression. So that will be posted soon. And to start with, we're going to start with a simple example of where there is no x. So right now we're doing y equals f of x plus epsilon. That's what we're going to be doing. How do you find the right f hat? We're going to start with the world's easiest baby example where there is no x. So y is something, and there is no x, and you just need to estimate what y is. And that is our first example, and it involves dice rolls. Here it is. So here's an example of a regression problem with only y and no x. So what we're going to do is we're going to play a game with these four-sided dice. And I brought in some four-sided dice for you guys. Let me see if I can convince the computer to let me show you the four-sided dice. What do I press? I press this. Press this. Will it work? I have to zoom out or something. Where's the dice? There we go. Okay, so here are some different dice that I brought in. We have the black one. This is the standard traditional one where the numbers are written on the side. The green one, the numbers written on top. And we have this funny blue one, which is a weird one. Okay, I think the black one sucks. I'm going to eliminate the black one. You guys can vote if you want to do the experiment with the red, the blue, or the green. Who's on team blue? Blue is cooler. One or two people. Who likes green? Green is cooler. Okay, 50-50. I'm the tie-breaking vote. I picked blue. Okay, we'll do blue. Okay, so we have a four-sided dice. And here's the game. All the sides are equally likely. You have to believe me that they're equally likely. They're all symmetric. They're labeled 1, 2, 3, 4. Step 1, you choose any number you want, y hat. Y hat is you're trying to estimate what's going to come up. So it's the hat. You choose y hat. And then step 2, we're going to roll it. And then we're going to call the outcome capital Y. Okay? And then step 3, this is my favorite part. You pay me y minus y hat squared dollars. Okay? So you all pay me. So everybody write down what you think y hat is, and then we're going to roll the dice. So everybody write down what you think y hat is, and then I'm going to roll it. Okay, so step 1, you guys write it down. Step 2, maybe I'll do one just for fun as well. Okay, here's what I wrote down. I guess nobody look at it. Don't peek. Okay, we gotta hide it. I'm gonna hide it behind the chalk. Okay, then no one will see what I wrote. Okay, there we go. All right. Okay, here we go. Rolling the dice. 1. All right, now everybody please stand up and give me 1 minus y hat dollars. Everybody has to pay me 1 minus y hat squared dollars. So whatever number you wrote down, you do 1 minus that, you square it, and please open your wallet and pay me. No, don't actually. Okay, so how much do I have to pay myself? I said y hat is 5. So I'm going to pay myself 1 minus 5 squared dollars, which is $16. Ooh, pretty big bill, because I was quite a bit wrong. Did anybody have 1? Did anybody escape? Yeah, all right, congratulations, you escaped without paying me anything. And the question is, what is the best value of y hat on average? So of course, the best value for this roll was 1, but let's pretend we repeat the experiment many times. What is the best value on average? I want you to calculate that. And then, this is a true or false question. You think you can prove why yours is the best. So you might have an idea of what is the best, but not really be sure why it's the best. So that's true or false. And then one more, this is like the bonus problem. The minimum amount of money you will pay me, even if you pick the best y hat. you will owe me some amount of money on average. How much is that? This one maybe is a little tricky. If you can answer this one very well and figure out the answer, great. If you did that and you're like, oh, this is boring, then work on this one, try to do it. Otherwise, put 5, 4, 3, 2, 1 for that one. And I'll give you guys like 4 minutes, say, to think about it. Feel free to chat with your neighbors for this one as well. You might not remember some of the probability things. You might need a little jog. This is what we said you would need last class, and now we're using it. So try to do it. See if you can do the proof. No, you pick any number y hat. Yeah, I guess it should be a real number. If you want to pick a negative y hat, that's fine. Yeah. Okay, 1 minute left. Try to, at least make a guess for the y hat, even if you don't get to the how much you will owe. Okay, 3 seconds left. Put in your guesses. Feel free to use 5, 4, 3, 2, 1 if you ran out of time for one of these, especially the last one. Okay, so here is how I would do it. I'm gonna do it first. So we're trying to estimate the dice roll. Okay, and how much you owe me is this quantity y minus y hat all squared. That's how much you owe me for a given value of y. So like if it comes out 1, that's what you owe me. What we actually want to do is look at the expected value of this. So this is how much you owe me on a particular flip, but the best choice in the long run would be looking at the average value. And we write average values with a big fat E like this. E stands for expected value. Expected value. Expected value. And this is what I briefly mentioned last class we would be doing today. Expected value. So that's what E stands for. So for any given value of y hat, you can calculate what is the expected value of y minus y hat. And you want to make this as small as possible, right? Because you want to pay me the least amount of money. So whatever this is, like the average is going to average over the values of the dice roll. Sometimes people write E sub y, and that means average over the value of y, over the 4 possible values, and tell me how much you owe me, and it will depend on y hat. So if it depends on y hat, it's going to be some function of y hat. I'm going to call that function L. And I'm going to write it like this, L of y hat. What does L stand for? L stands for loss. Loss. And that is how much money you're losing when you do this, right? So for a given value of y hat, this is how much money you're losing. That's called the loss function. And some people, in this case, it's actually the square loss. We'll see why the square loss is important later, but that was given to us in the problem. So the question is, you have this function, find the minimum value. And one way you can do it, that is very simple, is you can use the formula for expected values, which are, you just go over all the possibilities, and you figure out the probability of each possibility, and you add them all up. So for example, it's 1 minus y hat squared, with probability a quarter. So 1 minus y hat squared. When the dice comes up a 1, you owe 1 minus y hat squared. This has probability a quarter. And we're going to add that to what happens when the dice comes up 2, 2 minus y hat squared, and so on, plus 1/4. 3 minus y hat squared plus 1/4 times 4 minus y hat squared. So a very valid thing to do. And now if you're industrious, you can expand these all out. These are some quadratic equations. This is like a problem you could give to a 10th grader, and assuming they didn't walk away because they got bored, they would eventually be able to do it. Okay? This is going to be some equation, and you want to find the minimum. Not only is it some equation, it's going to be a quadratic equation. How do I know it's a quadratic equation? Well, it's a sum of quadratics, and a sum of quadratics is still quadratic. So let's do a little plot here and see what it looks like. So this is everybody's favorite graphing calculator, Desmos. Who's heard of Desmos before? Okay, if you haven't heard of Desmos, we're going to be using it a lot, so get to know Desmos.com. It's this beautiful graphing calculator where you can do sliders and fun things like that. Let me make this a bit bigger. Okay, and what did we say the function was? 1/4 times 1 minus x squared. Okay, so Desmos will only let you input x as the value. So we're going to replace y hat with x. Let's see what this looks like. 2 minus x squared plus 1/4. 3 minus x squared plus 1/4. 4 minus x squared. And assuming I typed in 1/4 correctly, that'll be the right thing. Okay, so that's the equation. That's the loss function. On the x-axis, I have the value of y hat, which is maybe a little bit funny. Whatever you choose, how much will you pay on average? And there it is. It's a quadratic equation. And it has a nice minimum. It's a quadratic equation with a nice minimum. And the question I was asking you is, what is the best value? What is the minimum of the loss function? And the nice thing about Desmos, if you click on it, it should tell us the minimum. Click. Okay. So it says 2.5, 1.25. So the minimum is going to be at 2.5. The best possible value you can pick here for y hat is 2.5. And the amount of money you will pay, the expected value of the loss when you do 2.5 is 1.25. And that is what I asked you on Mathematize. So let's see if people got it right or wrong. Reveal. So y hat, we had a lot of people pick 2 or 3, so maybe you didn't know you could pick an in-between value. If you pick 2 or 3, right, you are going up here. And you owe a little bit more money, right? So if you pick 3 exactly, let's see if I can get 3 exactly, then you owe $1.5 on average every time you play. But if you pick 2.5, you only owe $1.25. So 2.5 is a little bit better by 25 cents than 3 or 2. Okay. 6 people got 2.5. 2.32, maybe you did it like numerically or something. And the minimum amount you will have to pay me is this 1.25, 5 quarters. Did anybody get that one right? 5 quarters. No one got it right. Okay, so let's see how we can do this. So the way I said you could do it is you could do a big expansion and figure it out. But there is a faster way. There are tricks, and these tricks will be very useful for us. So in the last few minutes here, I'm going to derive the formula, how to simplify this without doing nasty algebra. Simplify with no algebra. Simplify. That's one way to do it, but we're going to do it starting from here. We're going to take this expected value, and we're going to use properties of expected value to simplify it directly. And that simplification is going to be the same trick that will be used when we do the bias variance decomposition, which is an important thing to understand. So this is not just some exercise, this will be a useful trick for helping you understand how these machine learning systems or how data science systems work. Okay, and here's the trick that we're going to do. I'm going to use a version of Pythagoras. This is the heart of the trick that I'm going to show you today, is Pythagoras. So Pythagoras, the normal Pythagoras says c squared equals a squared plus b squared, where you have a triangle with lengths a, b, and c. That's the normal Pythagoras. I'm going to do a Pythagoras for random variables. For random variables. Okay, so maybe I'll also draw the picture. So regular Pythagoras is you have this ABC. Let me draw the triangle over here. So you have C, and you have A, and you have B. If you think of them as vectors, you would write C equals A plus V as vectors. And then Pythagoras would say the length of C is the length of A plus the length of B, but only when you square them. C squared equals A squared plus B squared. That's the regular Pythagoras. Okay, in purple we'll do regular. Pythagoras for geometry. Right? And we're going to do Pythagoras for random variables. Let's do that in blue. Pythagoras for random variables. So now A, B, and C, instead of being vectors, they are going to be random variables. And it's still the same C squared equals A squared plus B squared, but it's not as random variables, but as the averages. So if you take the expected value of C squared, and you take the expected value of A squared and the expected value of B squared, that is how they add up. The expected value of C squared is going to be the expected value of A squared plus the expected value of B squared. And this is great. This is like the kind of thing we need because we have the expected value of something squared. So if we can write the something as the C, then we can split it up into an A squared and a B squared. And then we'll see what is what. Okay, you need a condition, right? Pythagoras doesn't hold for any A, B, and C. You have to have the right angled triangle. And it has to be a right angle triangle, right? 45 degrees, no good. So the crucial thing in regular Pythagoras was this 90-degree angle. What is the crucial thing for the random variable Pythagoras? It is, so RV stands for random variable. If the angle, if the dot product between A and B is 0, then it works. And what is the dot product for random variables? It's the expected value of A times B. So if A times B equals 0, on average, then the expected value of C squared equals the expected value of A squared plus B squared, where C equals A plus B. So the expected value of A plus B all squared equals that. This is the Pythagoras for random variables. It's very simple to prove it. If you know the proof for regular Pythagoras, the proof is identical for this Pythagoras. You just, every time you do a dot product, you replace the dot product with the expected value of the product. This is called uncorrelated, by the way. Uncorrelated. This condition of having a dot product which is 0 is called uncorrelated. So you take the proof for the regular Pythagoras and you just convert it into a proof for this Pythagoras for random variables. And now we're going to use the Pythagoras for random variables to simplify this thing. So we had y minus y hat. I want to write y minus y hat as a sum of two things that are uncorrelated. And what I'm going to do is I'm going to add and subtract an expected value of y. I'm going to add and subtract an expected value of y. So I guess I'm doing a long arrow. Let's go all the way down to the next page here. So what I'm going to do is I'm going to take the expected value, and before it was y minus y hat, all squared. And what I'm going to do is I'm going to add and subtract the expected value of y. So I'm going to do the expected value of y minus the expected value of y. Right? I haven't changed the random variable. This is still the loss as a function of y hat is equal to this. I've added and subtracted the same thing, so I haven't done anything. But now it has two parts. This part we'll think of as the A, y plus y hat. No, I want y minus y. Let's do subtract and add. Minus this. I think of this one as a. Think of this one as b. And now I've written the expected value of a plus b all squared. If it was true that the expected value of a times b was 0, then I could apply the Pythagoras. So is it true that the expected value of a times b is 0? So side quest. The expected value of a times b is what? It's the expected value of y minus the expected value of y, right? That's a times something, times b. I bumped the chord again. Okay, good pro tip, don't bump the chord. Times b. And b is a number. It's the expected value of y minus y hat. The expected value of y minus y hat, that's just a number. And numbers are not random. You can pull that number right out. So it's the expected value of y minus y hat. Okay. And because you do the expected value of y minus its expected value, well, you've already subtracted off the expected value. So maybe if you want, you can do a little more algebra. But this thing is definitely going to be 0. The expected value of y minus its expected value is definitely 0. And now we've checked the two random variables are like they're at 90 degrees to each other. They are uncorrelated. Whether this thing is positive or negative is uncorrelated with this thing. And now we apply Pythagoras. So by Pythagoras, this is the expected value of y minus the expected value of y squared plus the expected value of y minus y hat squared. And I left out the expected value. It should be the expected value of this, but there's no randomness, right? This is just a number. So you don't even need to write the expected value. This is the expected value of b squared, expected value of b squared, and this is the expected value of a squared. Okay. And this reveals what is the best possible value of y hat. We have some number that we're adding on to something minus y hat squared, right? So if I go back to Desmos, right, I have something of the form, let's call it v for the first one, and let's call the second one e for expected value. E minus x all squared. That was my equation. Whatever the first thing is, call that v, and then we'll do e minus x squared. Okay, don't do e, because e is already a number. Let's do a. And I'm going to tell Desmos, please add sliders. And you can slide these things around and see how things change. So the first number is just setting how up and down the parabola is. The second number is just setting how left and right the parabola is. Okay? The second number a is a, whatever it was, a minus the y hat. And the y hat was just the expected value of y minus y hat. So the correct answer here is whatever the average number on a dice roll is, that's what we want. And the average number on a dice roll with 4 sides is 2.5. It's 2.5. So a should be 2.5. Okay? A is 2.5. So the expected value of a dice roll of y is equal to 2.5. This is a good exercise to check y. So you should be able to prove this. Check y. That's a good check for you. This thing has a name as well. So 2.5 was the expected value, the average value. The thing that I've circled over here. The expected value of y minus its expected value squared. This comes up a lot and it has a name. Does anybody know what the name is? It's the something of y. Someone said it. The variance. This is the variance of y. This is called the variance of y. And it turns out that the variance of a dice roll with 4 sides is 1.25. And that is another good calculation for you to do. I can post a little solution for you, but it is you should try to do it on your own to see if you can do it and understand what mean and variance are. And that's 2.5. That's why I called it v over here. So this thing is 1.25. Well, not 1.5, 1.25. And now you can see the equation we started with, the expected value, is the same thing as v plus a minus x squared. V is the variance, 1.25. A is the expected value, 2.5. They're the same equation. That is how we minimize the loss. Okay. That whole example is a y value with no x's. We're going to build on this and do y values with x's. And we're still going to be looking for the expected value, and that will become clear next class. So we'll pick it up there. I'm a few minutes over. Thank you for your patience. Make sure you watch those videos. I would really try to do these calculations. If you can't do them, then go back and learn what an expected value and a variance are. I'll also post some solutions. Okay, see you guys on Thursday.